Hello everyone and welcome to this new web series from Anritsu focusing on pulsed measurements. This web series will basically comprise of 6 videos in which the first 2 videos will be explaining everything about how to make pulse measurements, why are pulse measurements important, what are the various applications where it is mandatory to do pulse testing. Normally, pulse is basically used in radar applications, but as the time has progressed, we have seen the applications of pulse measurements in various systems and subsystems as well. Having said that, radars are still primarily using these pulse measurements and the capabilities or the pulse technology. In this web series, as I mentioned, the first 2 videos will be explaining everything about why pulse measurements are important and what are the various applications and what are the basics of the pulse measurements. The rest of the web series will basically give you a live demonstration of how the pulse measurements are done and what are the main measurements when it comes to doing testing on active and passive pulse systems. We will be touching base upon how the biasing for RF or DC and IV is concerned, what are the various applications on wafer, what is the relationship between time and frequency domain when it comes to making pulse measurements. We will also be showing you key pulse parameter measurements like point in pulse, pulse to pulse, pulse profiling as well. This series is going to be very interesting because, as I mentioned, even today we have been hearing a lot about the 5G beamforming. Now, beamforming is something which has been there in the radar systems for a very long time. So it's nothing new. The technology was always there, but we were basically using it for radars and in the pulse domain. As you can see on your screen, we have an Anritsu vector star here. We have VNAs extending to a frequency of 220 GHz. We have various models ranging from as low as 70 kHz and in various versions of frequency models like 20 GHz, 40 GHz, 70, 110, 145 and then 220 GHz as well. In the bottom screen of this display, you can see we also have something called as a pulse modulator test set, which can actually come in 2 variants, one covering up to 40 GHz and the other one up to 70 GHz. Anritsu is the only one who can have or provide a pulse modulator test set covering a frequency range of 70 GHz. Moving on, the agenda of this presentation and the web series will basically be beginning from the very basics, so that even the beginners in the pulse domain can actually benefit from this presentation. We will be doing an introduction to basics of pulse measurements and their applications. We will also be talking about the measurement methods which had been there for a very long time and what are the new methods which have come up thanks to the technology that we have today in the changing world. We will also be focusing on various solutions as to how the pulse measurements can be done accurately, because there is a lot of time, because pulse is basically like an on and off switch, kind of thing, which makes a system work under pulsed condition. So if I talk of, say, radars, and I will be talking in very detailed manner about radars as well, radar has a lot of components, active and passive both. Now these components, if such high power, because the range needs more power, if the components are made to work on a very high power for a very long time, say a CW signals, then they would actually behave very differently. So it is a must to test all the components in a system, or in fact for that matter for a subsystem in the pulse conditions. We will, as I already mentioned, we will be doing 5 demonstration videos for making pulse measurements, and you will be able to make a difference or view a difference between how resolution matters. If your system or the measuring system has a capability of measuring very fine pulses to a resolution of 2.5 nanoseconds, you can actually see a lot of ringings and a lot of overshoots that might actually damage some of the components of a system or a subsystem, and you can then actually work to make things better. But if you don't have a system of finer resolutions, then you may not be able to see those ringings and offshoots in your pulse, and then you just can't take preventive actions. As I mentioned, we will be showing you a live demonstration of pulse profiling. We will also be showing point in pulse and pulse to pulse measurement capabilities as well. There is a very specific application wherein independent receivers are required for measuring duties which either have long delay lines in them, or in fact if there is some filtering in a particular subsystem, then the transmit and the receive side, they have some delays on the measurement side, and that offset makes a lot of difference in the transmission measurement accuracies. So that's why it is very important to have independent receivers for VNA making pulse measurements. But moving on, let's talk about the applications which require basically pulse measurement capabilities. So the applications basically for pulses are huge. The first and foremost application is for defense, because these guys use radars a lot, and then also for electronic warfare systems. Nowadays we are seeing a lot of medical applications also for imaging applications. So there are some people in the medical domain who are using VNAs to actually see if there is a like a kind of a tumor or a tissue accumulation, and for that they need pulse system, and they can actually do an imaging of the human tissue as well. So also on the electronic applications, as the devices are going smaller and smaller, these devices actually come on a small silicon wafer, and these devices cannot be worked upon with the CW signal for a very long time. They need pulsing either on the RF side or on the IV or DC side. So even the electronics is seeing a lot of applications for pulse capabilities. Now general applications definitely are there. So you have speed radars, car radars, the weather radars is something which has been there for a very long time, and even those radars actually they use CW signals, but we are seeing some activity even for pulse as well. On the device characterization side, also for active amplifiers, filters, and also for on-wafer testing, you need a system either being biased in pulse or like RF or in IV. In the communication industry also, you have to do some test in the burst mode. So what burst mode basically is, that you send in a lot of small bursty signals to your device under test, and then you see or analyze the response that device has on these input bursts coming. For the automotive industry, this is one of the hot topics of today, and automotive radars have taken a huge leap. So even automotive radars are very important for that. And then we do have antenna measurement system also working under the pulse mode, and of course the radar cross section, wherein the receiver gating is definitely required, is amongst the applications. So you can see the applications are numerous. On the right hand side, you can actually see some TR modules, and on the top you have a radar working, and then you also have silicon wafers. Some traveling wave tubes of high power also need some kind of biasing. So as I said, the applications are huge, and that's why whenever you are designing a system or a subsystem which works under pulsed influence, it becomes very important that you actually test the entire system even in the same conditions. Moving on, there are some basics that we need to cover on the pulse characteristics and the definitions. So as you can see, basically a pulse is is a kind of a small packet of energy which is on for a shorter duration of time and off for a longer duration of time, and those definitions we will also cover. But as you can see from this diagram, there are some key important terms like the rise time, and there are different percentages associated with the rise time, like 10% rise time or 90% rise time. And then on the top you can see there is something called as an overshoot. So you can see that from the average power highest contained in the pulse, there are some overshoots associated with the pulse. Now these kind of overshoots actually can destroy or damage the DUT when it first comes under the influence of a high power pulse, there. So it has on time, it has off time, there are peak power, and then there are droops as well from the average power of the pulse, and then you also have the fall time. So basically this is just a definition. Of course, if you need to go into very details of what pulse measurements are and what duty cycles, what's the meaning of PRI, although we'll be covering that, but you can always Google it. All the information regarding to pulse basics and the definitions are all available there. Moving on, it is very important to first understand actually how what is the relationship of a pulse in frequency and time domain. So this is one of the mathematical tools that I downloaded, and on the top you can see that you can you have a pulse, and with this software you can actually increase or decrease the pulse width. So as I increase the pulse width, you can see that the spectrum content actually narrowed down, right? So if I consider this pulse right now, you can see that the spectrum content is very low because the pulse width is really high. But let's see, if I slowly and steadily reduce the pulse width, that means my pulse is getting narrower and narrower. So as the pulse get shorter or narrower in the width, actually the spectrum content keeps on increasing. So that means narrower the pulse, the spectrum content of that pulse is gonna be very huge, right? So this is something which as far as the measurement is concerned, these things should be kept in mind, because this plays a very important role when you're trying to characterize a particular pulse. So to shorten the answer or shorten the basic, shorter the pulse width, higher the spectrum content, or more the spectrum content, and wider the pulse width, lesser is the spectrum content. Now moving on to one of the major applications of pulses is basically a radar, and I don't need to explain what radars are, but just to give you a visualization, you can see that there is a transmitter, and then that transmitter basically sends in a pulse, and then when it hits a particular target or any object, there are some reflections happening, and when these reflections come back to the TX-RX system of the pulse, then you can see that there is an echo, right? So this is how basically anybody, or basically the defense people, that is how they actually see how far a particular object is. So the range and the distance is basically what radar does. But apart from that, this piece of information is not sufficient. You need to know in which direction this particular object is flying in or approaching or is exiting. So for that, in the previous world, what used to happen was that these antennas which were kept on the top of, say, a military truck or somewhere else, they actually kept on rotating. And based on the azimuthal and the elevation angle, you could see that the amplitude of the reflection coming back becomes higher when that particular dish is basically seeing towards that object. So this is the basic principles of radar. This is how the ranging and detection is basically done in a radar. Now there are some very important key parameters, like how does somebody know that using this kind of frequency is going to be valuable for my application. Should I make an X-band radar, or should I make say an E-band radar? Which one should I make so that I can actually do my application well? So radars basically come into different bands. So you can see that in today's world, actually the radars have actually reached to a frequency of say 110 gigahertz and even beyond. There are some applications which are going on, but to keep things short, you can see that starting from very low frequencies wherein the wavelength is really high of the signals, the imaging applications wherein like if you are entering an airport, and I'm sure everybody has done that always, when you enter an airport at the time of checking in, you are asked to stand inside a small box and asked to actually keep your foot and hand in a particular position, and then there is a really fast scanning kind of object that actually scans the entire body. Now those kind of radars basically use frequencies as high as 110 and maybe sometimes more. For that matter, the automotive industry, the car radars, which are there now in the talks a lot, they are basically working in the range of say from 65 to 70 gigahertz, some of them, but basically the E-band. So you can see that there are various applications, and now the fact is that with like if you have really low frequencies, that means the wavelength is really high. So for low frequency kind of antennas, the size of, or the low frequency kind of radar system, the antenna size is bound to be very huge. So if you see the bottom of this image, you'll see that some of the radar systems are actually equivalent to like a big garage door kind of radar system. But as and when you keep on increasing the frequencies of them, since the wavelength is very short, of course the distancing comes to a compromise, but then the size of the entire subsystem or the entire system becomes very small. So you can see that the E-band radar, car radar kind of stuff, they are really small in size, right? And as I discussed on the airports, now there are so many elements. Now the reason why those things are so big is because of the fact that the area of human scan body is high or huge. That's why they are bigger in size. If I want to compare what are the major parameters that I should keep in mind when I'm trying to design a radar is, if I want really high resolution kind of thing and my application is very small range kind, then the smaller the wavelength, the smaller the object the radar is able to detect. So the resolution is very high, and that's why the high frequency radar systems are basically used for imaging kind of application or close communication kind of thing. And of course, higher the frequency, smaller the antenna size, and with the same gain. So the advantage that you have with higher frequency radar systems is that they are, number one, small in size, number two, there is no compromise on the gain of the antennas, and number three, they are lesser in cost as well. Now radars have different classifications as well, as you would see from this image, that radars are basically into two categories, CW and pulse. But in the pulse domain, you have non-coherent and coherent, and then these are various applications again. So low PRF means low pulse repetition frequency. So that means the on and off time from one pulse to the other, that is called as the PRF. And depending upon the PRFs, the pulse repetition frequencies, or you can call them pulse repetition intervals as well. And based upon the 2D cycle, based upon the pulse width, the applications are humongous. So what kind of radar measurement system you are trying to make, it will have different applications. And these are some of the examples that I wanted to show you. On the left hand side, you basically have an X-band kind of radar systems, and you can see that from this image, it's like a big huge stop signage kind of antenna, and there are a lot of elements at the back side as well. And on the right hand side, you have a very small kind of E-band automotive car radar kind of system, which is really small. It can basically fit in a small backpack. Moving on, as I showed you in my last slide, in the past, if you wanted to know the elevation or which direction a particular object is approaching towards you, or maybe it's going away from you, there was a rotor motor which used to keep on revolving in 360 degrees, and that is how you would come to a conclusion that okay, this is coming from that direction, east, north, west, But as the time has progressed, the beam steering basically has gone the electronic way. And that is what also happens now in the 5G communication system, in which the beamforming happens by a phased array antenna. Now the same concept also applies for radars. So just to give you a definition, and you can actually read through it, but it's pretty straightforward, but I'll still try to be a more explanatory on why phased array antennas are used. So the statement that I had from one of the websites is that a phased array antenna is an array antenna whose single radiators can be fed with different phase shift. And this will become more clear from this image, and you can see that as a result, the common antenna pattern can be steered electronically. So what you see from this particular image is the fact that if all the phase shifters are at an angle of 0 degrees, then the beam is just looking at the forward direction. But the moment I introduce a phase shift between these elements, you can say them elements because these are basically antenna elements. If I introduce a phase difference, then this beam can be steered into other direction, and this is what normally happens nowadays with the radar systems, and in fact, for that matter, the 5G base station and the antennas that you are seeing. This is the basic principle. Now these phased array antennas can come into basically two fashions. One is the linear array and the other is a planar array. In the linear array, you can see that they are controlled by a common single phase shifter. At the backside, you can see that there is only one phase shifter, right? So but still there are so many antennas and there are so many components that you ought to test each and every component very wisely, because what can happen in these circumstances is the fact that even if one of your component or one of the phase shifters or one of the antennas is not working properly, then the beam steering will go for a toss, and then the whole system actually can become inconsistent. So that's why testing of these phase array antennas and all these active and passive components that form a subsystem of making these radar measurements are very important. In the planar array, you can see that each and every part, or you can see that these phase array antennas consist completely of single elements with a phase shifter per element. So that means per element you have a phase shifter, and that's why these systems even become more complicated. Now the advantage between linear and planar is that planar and can actually work a little better because it has one phase shifter per element. So even if something goes bad with one of the components, the system will still work. But with the linear arrays, if the one phase shifter which is taking care of the entire system, if that goes bad, then you are running into trouble. But I just wanted to introduce what phased array antennas are doing and how the beam steering actually happens. So what are the pulse now that we have a good understanding of what radars are and what are the pulse basic parameters, what are the basic applications. Now let's try to correlate what are the basic pulse parameters that can affect your application. So first is the pulse width. Now the pulse width is very important for range resolution. Now when I say range resolution, it's basically the ability of a radar system to distinguish between two or more targets on the same bearing but at different ranges. So this is very clearly defined in the images below, as you can see. Now these images, what I've done is, because I couldn't find a better image to explain, instead of reducing the pulse width, because I couldn't find a better example, instead of reducing the pulse width, what I did was I increased the distance between the two objects. So in the first image on the left hand side, if your pulse width is say roughly around 1 microsecond, then you can see that if there are two targets which are at a spacing of 100 meters, you will only see one reflection coming back, because the wavelength is roughly around 300 meters, right? But if you have two systems or two targets which are at a distance of 200 meters, then you will basically see two reflections. But talking of the other side of the story, even instead if the spacing was not more between these two targets, if I had the ability to actually reduce the pulse width to a very narrow pulse width, then in fact I can actually do a better resolution, even if there were 10 or 12 targets in the same direction with a distance of say 5 meters or 10 meters as well. So pulse width, narrower the pulse width, the better range and better resolution you get. In that sense, the narrow pulse width also have like the energy content is not that much, but there are techniques by which, like modulation techniques, by which you can actually still have a very narrow pulse and still the range can be really high. So pulse width determines range resolution. So there are few comments and conclusions that I wanted to give on this slide. So a wide pulse width generally provides better range but poorer resolution. So you can see that, because okay, the energy content in that pulse is really high, but since it's really wide, so its resolution is not good. But a narrow pulse width has lesser range but better resolution. So this relationship basically is what the designers mostly they want to do a compromise between these two. But there are pulse compression or you can use a modulated carrier in the narrow pulse width kind of domains, and then you can still achieve really good ranges and resolutions as well. The second important parameter is the PRF or the PRT, so pulse repetition frequency or pulse repetition time. And then this gives you or the best way that I could explain the effect of varying PRF and PRT is an example of synthetic aperture radars. So on the left hand side, and this is basically used by airplanes. So since the ships they are really slow moving kind of thing, so if there is a airplane who has this synthetic aperture radar, what basically happens is whenever this plane is flying above any say enemy territory, what they can do is by varying the pulse repetition time, they can actually image exactly as to how the particular ship is looking. So this is very evident from this slide on the right hand side. You can see that it's using basically 8 different types of pulse repetition time. That means the on and off signaling of the pulse is varying with every transmit that this radar does. So by that, every time they send in different pulse, they get better and better resolution of the target. So pulse width, PRT, PRF, these are the two main important kind of applications or measurements that are normally done. Now, the reason that I'm telling you all those things is because of the fact that since there are so many applications which are related to varying the pulse width, the pulse repetition interval, the duty cycle, it becomes very, very important for a designer or a manufacturer to actually test all the components which will form these kind of devices, like synthetic aperture radar, or like a normal defense radar, or any other application which works under pulsed conditions. Now that we have talked of a lot of applications and what are the various important parameters, let's come to the measurement methods that have been there for a very long time in this industry. So this particular image, you can see that on the left hand side of this image you have a wider pulse width, and as I mentioned in my initial talks in this presentation, the wider the pulse width is, the narrower is the frequency content. And on the right hand side you can see that there is a narrow pulse, and that's why the frequency content is really high for that pulse. So primitively, the traditional methods is that for the measurement system, normally the instruments are limited by a receiver, or I should say IF bandwidth of 5 to 10 megahertz, right? So if there is a pulse which has broader or wider spectrum, that means if there is a narrower pulse, then the entire spectrum content cannot actually be processed by the measurement systems. I'll come there, but let's see what happens in the traditional method. So if the pulse width is really wide, then there is no problem, because the spectrum content of the entire pulse can be processed by the measurement system, and that method was called as wideband method, wherein we were doing a direct sampling. But the problem here is that we could only measure limited pulse width, right? With this direct method or direct sampling, if the pulse gets narrower, then the spectrum content actually widens, and then you cannot do direct sampling. So there would be a compromise. So with the wideband method, you could only characterize your system, or DUT means device under test. You could only characterize your devices for a certain pulse width, which is really big. But there were some methods, and in fact some of the people in the measurement world still use these methods, and these are called as narrowband methods. So that means you have a narrow pulse width, and the spectrum content is high. So the only way of doing measurements is that you actually filter all of the frequency component, but just keep the central spectral frequency, right? But the problem there is that if you do that, then of course you have a dynamic range penalty, and then there are some features that you just cannot do with narrowband kind of method. And this is an explanation of what happens when you basically filter out all the spectrum content of a narrow pulse. And what happens is, when you take out everything, since in a pulse the power is distributed, the entire power content actually goes for a toss, and the signal to noise ratio actually becomes lower. And you ought to have dynamic range reduction of the order of, if there is a 1% duty cycle reduction, that basically leads to 40 dB of dynamic range reduction. So that means there are a lot of things that you cannot do with this narrow band method. And the reason that I'm explaining all these things to you is the fact that in today's world, the pulses are actually going narrower and narrower. And the reason for that is, people want to use radars not only for defense applications, but as I told you, medical application, close range communication. 5G is a classical example of basically 5G is beamforming, but still the automotive radars, they want to have really good ranges as well, and resolution, because if the car radar is not working well, and if it is supposed to give you an indication if there is a person standing in front of the car for the autonomous driving vehicles, if that system fails, then you have problems. So the gist of the story is that the new measurement methods or the new technologies for radar systems are using narrower and narrower pulses. They are using various or varying type of PRFs, basically narrower pulse and higher pulse repetition interval. That means the on-off is really fast, so that they can utilize a lot of other advantages that comes with narrow pulse. To actually cater to all these applications, basically Anritsu introduced a new option, and in fact, to be honest with you, it's not a new option. It has been there for a very long time, but since the radar industry has now grown up to an extent that it has, we thought we would want to revise these things. So Anritsu has something called as a IF digitizer option, and you can see that we are basically using ADC of 400 megahertz, which basically gives you 200 megahertz of IF receiver bandwidth. So that means in time we can resolute a 2.5 nanosecond kind of resolution. So that means our resolution is 2.5 nanoseconds. So you can see that we have 200 megahertz of receiver bandwidth. That gives us a measurement resolution of 2.5 nanoseconds. Now the reason why this becomes very important is the fact that, as I told you, you need to characterize very narrow kind of pulses, and when you want to analyze these pulses, you want to actually dig really deep into these pulses, because these are very narrow pulses, and the power content, they are trying to improve the power content day by day. So even a small ringing or an overshoot which actually exceeds the power handling capacity of a particular, say, an amplifier or a filter of a subsystem, that can actually destroy the entire system. So that's why you need to very finely resolute these pulses. So that's why higher and higher resolution is basically required. Up till now in the industry, there are some methods by which you can actually reach to, say, 12.5 nanoseconds, but I'll show you what's the difference between a 15 nanoseconds and a 2.5 nanosecond kind of resolution window. We also have independent measurement IF receiver windows, and this also becomes very important. Because as I told you initially, if the device under test has some delays associated with it, and it has an input and an output port, now if your transmitting side of the VNA, which is basically the measurement system here, if the transmit side pulse goes inside and it takes a long time to actually come and meet to the port number 2, the two receivers are actually out of sync. And when they are out of sync, then the S21 or the ratio measurement can actually be affected, and I'll show you how that is very important. So having independent measurement IF receiver windows is very important. And then of course somebody would want to record the entire sequence which is happening, so we do have a 500 milliseconds of record length as well. Now this is something that I wanted to show you. So if you have a measurement system which has, say, a resolution of say 15 nanoseconds, so if you are trying to characterize a particular pulse with a 15 nanosecond kind of resolution of your measurement system, then you would see that pulse in the color of green, and you can see that if I'm a measurement person who is dealing in with radars or pulses, then I would say, okay, with 15 nanosecond resolution everything looks good, so no problem. But actually inside that pulse there are a lot of things which are happening, and since my measurement system does not have that kind of high resolution, I see no problem. But the moment I have a 2.5 nanosecond kind of resolution, you can see that the same pulse basically has a huge overshoot associated with that. And now the moment you will plug this, say suppose with the 15 nanosecond resolution you were really happy that everything is working fine, but the moment you would attach your DUT like actual duty to this system, it might actually, you know, cause some problems, and it might cause burns out to various subsystems. So it but with 2.5 nanosecond resolution, you can see, oh, there's an overshoot, and that's huge. So you would first try to take countermeasures, and then you can proceed further. So having a resolution of 2.5 nanoseconds, and this 2.5 nanoseconds we can only get because of the 400 megahertz ADC that we have in our option 35, which is IF digitizer. So that's why having a higher resolution system is very, very important. Now, when you want to drive or test your duties with a pulse system, of course you will need pulse generators, right? So in our vector star, which is the highest performance vector network analyzer that Anritsu has, you can see that there are 4 pulse generators: PG1, PG2, PG3, and PG4. So you can actually use these pulse generator to send in a pulse signal to your DAT, and with these pulse generators you can basically do a lot of other stuff, which I'm going to tell you in the next few slides, wherein you can do a singlet, you can transmit a singlet pulse, a doublet pulse, triplet, quadruplet, and even for that matter a burst kind of signal as well, to characterize various subsystems. Now, if you don't want to use the internal pulse generators, and if you have an external pulse generator, then you can also use the sync or the pulse inputs that we have on the backside. Pulse sync is what we call them. You have in and out of them. So that means we also support external pulse generators. So the 4 internal pulse generator are very, very important, and on the right hand side of this slide you can see that there's something called the pulse view configuration. Now you can see that basically the 4 pulse generators can be actually used to have or output any kind of pulse which is required. So you can see I can actually send a pulse train, I can send a doublet, singlet, I can send a pulse mode, burst mode as well. And on the B2 profile is basically the measurement profile. So as I said, you can send in a singlet, a doublet, a triplet, a quadruplet, and in fact for that matter a burst as well. So you by default get the pulse generator in the vector star. On the measurement side, as I already explained, and I can explain further as well, there are 3 to 4 main important measurements when you are dealing in with pulses. The first one is called as a pulse profiling. So by pulse profiling, you basically are sweeping time, and then you can see that, okay, what kind of pulse or what are the characteristics of the pulse. That means you can measure the rise time, the fall time, the average power, everything you can do with the pulse profiling. The pulse to pulse measurement capabilities, if you have a train of pulses, you can actually select one particular section of pulse number 1, and then you can compare how your DUT is behaving for a number of pulses in that same segment. So that is what is basically pulse to pulse, and all these things that I'm explaining here, I have covered them in details in a video demonstration file in this lecture series. And then the point in pulse is basically if you want to analyze a particular point in a pulse, and you really want to dig deep as to what is happening inside that pulse. So basically, if you want to measure pulsed S parameters, you would want to sweep frequency, and you can also sweep power while doing a point in pulse. So these 3 are the main ones, but we also have something called as a continuous point in pulse and a continuous profiling, in which in one single acquisition, the response that the DUT is giving for a particular pulse for a very long duration of time can actually be characterized, and this is only available with Anritsu. If you're interested to know more about these 2 functions, you can always send us an email and we can help you out with the demonstration. Now coming on to the another topic which is related to pulsing is basically how do you actually do a pulse or let me put it this way. If you have a DUT and say an active amplifier, all right, now there are different classifications of amplifiers. Some of them you can actually give them a RF pulsing, or you can also give them DC bias, or in other language you can also give them DC or IV kind of pulsing. So on the left hand side you can see that if there is an amplifier and I'm just trying to give them a pulsing on the RF side, then I need a pulse modulator which can do the pulse modulation of the source, which is basically on the left hand side you have a CW source, and then by attaching this pulse modulator test set you are actually switching on and off this switch, and that is how you are trying to, or you are giving a pulsed RF to as input to this amplifier, right? So you can do that. And for on wafer devices you can actually provide a pulsing by giving a DC bias, right? So you can also pulse the bias, or in some cases you can even have the RF and the bias both as pulsed. And there are various combinations associated with different kind of devices, but again Anritsu has solution for both of them. We have pulse external pulse modulator test sets, we have internal pulse generators, and we can do a complete characterization of any of your pulsed applications. As I mentioned, we do have pulse modulator test sets, and you can see that two of them are actually covering 40 gigahertz. So the reason that we have two of them covering 40 gigahertz is the fact that you have only source modulators with one option. As you can see on the left, SM662, it has two source modulators, but the other model, which is also covering up to 40 gigahertz, it has two source and two receiver modulators as well, because sometimes it so happens, say in a pulsed antenna kind of applications wherein the transmit and the receive antenna are very closely spaced, so you need to receive you need to gate out the response of the receiver of the second one by a certain extent. So that's why you may need a receiver modulator also for that particular antenna to do the receiver gating. So you could do that, and the same thing happens for 70 gigahertz as well. So this is about the first presentation or the first video as an introduction that I wanted to give you. Please watch the complete video series of the pulse measurements from Anritsu. There are basically 5 to 6 videos. You may have to spend a little time to understand all these things, but this will actually help you a lot while you are doing your pulse measurements. So if there are any questions or queries, or if you want me to cover any of the other aspects of pulse, I mean, I could really go deep into the pulse basic features as well, but I thought this is a good introduction of the pulse measurement system and the pulse capabilities. So thank you so much for tuning in, and I look forward for you guys to see our next videos. Thank you so much.